Greetings, fellow learners. In this video, we are going to work on back propagation by hand. So we're going to walk through a specific example and perform all of the computations from start to finish for a single iteration so that you get an idea of how back propagation works. Now, a note here is that I feel like the main way to learn these computations is to perform them by yourself, by hand, but hopefully this video will give you a general guidance in how to perform those computations too. So with that in mind, let's get to it. So high level, backpropagation, it is an efficient learning procedure to compute the gradient vector of a loss function of a neural network. And this in turn is used to update the weight parameters of the neural network. So here, this is a gradient vector. So it is a vector of all parameters, and each of these parameters are like weight parameters that signify on their own how does the loss change when changing the weight parameter a little bit, right? Now, together as a vector, though, it represents direction. So the gradient vector, when evaluated at a certain set of weights, p, gives the direction of steepest ascent at that point, p. And hence, calculating this gradient vector helps adjust parameters to minimize the loss. But computing the gradient vector is difficult as the number of parameters increases, as is the case with the neural network. And so we use efficient strategies like backpropagation to compute the gradient vector and hence update the parameters. And so we use backpropagation. And now with that preamble out of the way, let's actually walk through the backpropagation procedure for an example network that we see here. So in our network, we're going to have an input layer, some weights. There's going to be two hidden layers here, each of them with ReLU activations. And then we have an output softmax activation. So assuming like a calibrated neural network, we would see that this would represent something like the probability of getting a specific class. Now these are then going to be used in a cross-entropy loss function, since this is a classification problem, assuming so, in order to generate a loss. Each of these neurons here is a slightly complex since they're taking in inputs from multiple weights, and then they're also performing an activation function. So I'm going to split each of these neurons out. And when we do that, we get something that looks like this. So this neuron here is just going to be a sum of products of the input and weights here. Then we can apply a ReLU activation, and this is just simply the output of the ReLU activation here. Similarly, this is just a sum of products of inputs, and then this is the output of a ReLU activation applied on this neuron here. And this softmax, I've encompassed it to be all layers because it's a function of all layers. So we have this is going to be the softmax. That's a function of both of these neurons. And this is also going to be a softmax operation output of these same two neurons here, just with a different numerator. And then we can use this in our cross-entropy loss function to compute the loss. So this is the primary network that we will have and we'll be working through with our backpropagation algorithm. Now the goal here is to compute the gradient vector. That is how the loss changes with respect to all of these weights, and these weights over here. And to do this, first in our backpropagation step, we start at the end where we try to determine how changing this neuron output affects the loss over here. And that is quantified by this scalar quantity right here, which is partial of L divided by partial of Y pred 1, indicating the first neuron. Similarly, we do the same for the second neuron here. And then we move continuously backwards in order to get how each of these neurons affects the loss. And we would use the previously computed gradients over here in order to compute the new gradients over here. Exactly how we are going to see in, the computation process. And so we can also compute how changing the weights affects the loss, and then changing the previous neurons here. And we just keep propagating back from the layers here until we understand exactly how each weight here in the network is going to affect the loss. And once we do so, we are then going to, use that over here in this part here. It's going to give us like the direction of steepest ascent overall. Negative of that would be like we want to go the opposite of the direction of steepest ascent, so steepest descent. Learning rate is going to give the magnitude of change, and then we update each weight here in the network accordingly to this formula. And so overall, the idea is if we make all of these updates at the same time, we would generally move in the direction of minimizing this loss. Now, before we get into the actual details, let's actually walk through some useful math formulations. So for one here, the derivative of e to the power of x is e to the power of x. Derivative of log x with respect to x is 1 over x. Now, derivative of a function f divided by a function g of x with respect to x is given by this formulation, which is g of x times the derivative of f of x divided by f of x times the derivative of g of x, divided by g of x, the whole squared. Now, the last and probably one of the most important parts of this entire formulation that we're going to use is the multivariate chain rule. So if we have x, which is a function of a variable t, and y, which is a function of the variable t, and z, which is a function of x and y, then we could write that the partial derivative of z with respect to t is that of z with respect to x times x with respect to t, plus z with respect to y times y with respect to t. And this is the multivariate chain rule that we will heavily use in our back propagation formulation. And so if you kind of just have like a rough idea of just these formulae for now, I think you have enough knowledge to actually compute the back propagation of this simple neural network by hand. So let's get to it. So let's say that we're passing some input right now. So we have a sample, and the input sample is 0.3, 0.5, a two-dimensional vector that we pass as an input. Next, we want to actually compute what the activation is for this layer over here. So I'm calling this here like H1 pre and the ith neuron of that. So we have 3 neurons. So we have neuron 1, neuron 2, and neuron 3's calculation. So for example, this is just going to be a sum of products of the input activation times the corresponding weight, which is exactly what we see here, right? And performing the computation, given its initialization, we get negative 0.04, which we have written over here. Similarly, performing the computation for the second neuron, we get 0.04, which we write over here. And the third neuron, we get negative 0.16, which we write over here. Now, once again, I'm going to stress that the way to actually understand what is going on here is to write out this computation, do the math on your own yourself. But hopefully, this will be a good guidance in making sure that you're kind of doing things in generally the right way. Next, we perform a ReLU activation here. So a ReLU activation, it's going to be, the same as the input for inputs greater than 0, but it'll be 0 otherwise. And so for this first neuron in this layer, so the first neuron here, it's going to be the ReLU applied on this input. Since it's less than 0, we have the output as 0. The second one, it's the input is greater than 0, so it'll be the same as the input. Input is less than 0 for the third case, it's going to be 0. And so we write it out here. And next we perform the same sum of products here. So it's just going to be, this, and this, whatever information is going into here, you'll get negative 0.02. The math is over here. Similarly, you'll get 0.02 here and 0.02 for this third case here. Hope the math here makes sense. Now, similar to the previous case, we are applying a ReLU activation. So the input, which is negative, is going to be floored to 0. And then the other inputs are just going to be passed through. So we have like 0.02 that passes through here. And now this output is going to be, again, a sum of products, which, if you do the math, you'll get 0.032 over here, and then you'll get 0 over here. Next, we apply a softmax function to this input over here in order to get values here. And in order to perform a softmax, it's basically e to the power of one of these values. In this case, it's the output 1 that's here, divided by the sum of e to the power of each of these outputs. So that's e to the power of 0.032 plus e to the power of 0. And we get 0.508 here. And similarly, for this neuron, we'll get 0.492, performing the softmax operation. And if we now perform the cross entropy loss, which is negative of label times the prediction for what that label should have been, minus label for the second class times prediction of what that second class label should have been. So we are going to assume here that for this input, the label was that, hey, this belongs to class number 1. So that means that y1 will be 1, which is exactly what we see here, and y2 will be 0, which is what we see here. Performing the math, you're going to get 0.677 as loss, which we write over here. And this is going to conclude the forward pass for this single sample. So I hope it all makes sense. Next, now let's actually look in computing the backward pass. So first, what we want to do is, like we mentioned before, we take this neuron and try to determine how does changing this neuron a little bit affect the loss. So this can be, quantified by a gradient that's given by this right over here. And so the loss we know is this value. And if you take the gradient of that loss with respect to the prediction, the first prediction here, we see that, this is a constant y1, so we just leave it out, times derivative of the log of a value is 1 over the value itself, minus, this is going to be a constant with respect to y-pred1, so it doesn't change when you change it, so hence it's 0. And substituting the values and evaluating the gradient, we see that it is negative 1.97. So what this really means is that if you increase this value over here by like a single notch, like a very small amount, then the loss is going to decrease by 1.97 notches. So, if you were to actually perform the forward computation and just try and say, okay, if this is 0.508, this is the loss here, 0.67727. But if you were to just change this by increase it by 0.01, right, to 0.509, you would see that the loss is going to now be this value, which is negative, which is like 0.00197 less. So if you increase it by 1 notch, it decreases the loss by 1.97 notches. So this is like a nice little empirical way to just prove that whatever work that you have done here with this abstract gradient calculation actually works out to be true in real life. So it's pretty nice to just verify in this way. And also, I'm just going to represent the gradient that we just computed by this delta symbol over here above the neuron. And we'll keep writing that across all neurons as we compute the gradients with respect to changing every neuron. Next, let's move on to calculating the gradients for the second neuron. Now it's going to be represented by this value here, where if you perform the computation, take the derivative with respect to y-pred2, you're going to get 0 here. And what this means is that if you change this value of this, the output of this neuron, if it changes, the loss does not remain affected at all. And you can kind of prove this out too by just kind of varying this value just a little bit by 0.01, and you can see that the loss value does not change whatsoever. So again, that's empirically proving what we just computed over here. So it's just nice to cross-verify. So now we'll move on to this neuron over here. So how much does this loss change when we change this value of the neuron over here? That's going to be quantified by this delta L by delta O1. And to do so, we cleverly use a trick which is the multivariate chain rule. Right, and this helps us use previously computed gradients in order to compute the gradient at this point. So the intuition here is that, well, to find out how much changing this affects this loss, we can just use how much changing this affects the loss, and then multiply it by how much this neuron changes this neuron here, right? But since it's affected not only in this one path, but also in this other path, we do the same for the second neuron. So how much does this change affect the loss? And you multiply it by how much this change affects this neuron here. And then we sum their influences. And that's exactly what this chain rule is exactly doing. So let's actually walk through the computation. So we've already computed the first part of like how much, the loss changes with respect to pred1, that's negative 1.97, and how much the loss changes when you change this output neuron here, pred2, ypred2, which is 0 in our case, right? But now we have to compute these two values here. So let's actually walk through those. So in the first case here, you know that this ypred1 is going to be essentially a softmax activation. That's represented by this formulation here. And now what we can do is use the derivative of f of x divided by g of x. Now remember, that's going to be g of x times the derivative of f of x, that's over here, minus f of x times the derivative of g of x with respect to O1 over here. And divide that by g of x whole squared. So that's exactly what we're seeing here. And if you kind of like split this out, you can see that you can rewrite it in terms of y pred 1, times 1 minus y pred 1. Substituting the values, you get 0.25. Similarly, for y pred 2, we have like a softmax activation here. And you perform the same kind of calculation of, f of x by g of x. And doing so, you get like a negative 0.25 here. Now, substituting these values into our chain rule equation over here, you can see that you'll get negative 0.49201. So what this means is that by increasing O1, that is this output, by like a small notch, you will decrease the loss by 0.49 notches. And to verify if this is actually the case, you take the current loss, the current O1, you get the current loss. You just increase it by a small 0.01 amount, you'll see that the computed loss is going to decrease by 0.49 notches, which is exactly what we computed with our more abstract calculus computation here. So that's good. We were able to verify it. And so we write the gradient that we just computed over here. Next is we're going to now determine how does changing this output affect the loss. It is given by the gradient of L by that of O2. And here too we use the multivariate chain rule where we now need to compute these values here. That is how this neuron is going to be affected by changing this neuron, and how this neuron here is also going to be changed by affecting this neuron. So performing those computations in exactly the same way that we did before, we get almost the similar values of negative 0.25 and positive 0.25 for the second case. Substituting in our original equation over here, you're going to get 0.49201. So what this means is that now increasing O2, that is this neuron, by like a notch, it's going to increase the loss by 0.49. And that's exactly what we see when we verify this with, an example as well. So I hope all of this is making sense. Now we move on to the weights layer. So in order to see how does changing this weight affect this loss? So in theory, it just means that, we already know how changing this affects the loss. So now we multiply that by how this neuron is going to be affected by changing this weight. That's exactly what's given by this product over here. This is how the output neuron, this here, is going to be affecting the loss. And this is what we just mentioned of how changing this weight is going to affect this neuron here. And since we already have, that first term, we just substitute it here. It's negative 0.49. And the second term is simply going to be just, it's a whatever is the input itself, right? Because this is like a sum of products of the inputs and the weights. So if you take a derivative, it's just going to be the input here, which is given by h1 for the second layer. And since it's 0, you substitute those values. We can fill it in our table here. This is going to be the table that I'm going to be using to write down the derivative of the loss with respect to each of these weights. So for this first, there's like 6 of them, right? So first we have 0, which means that if we change this weight, at least for this example, it's not going to change the loss at all. Similarly, we can say the same thing is true for this second case, right? For the second weight, how does changing this weight affect the loss? Well, it's how changing this neuron over here affects the loss times how changing this weight affects this neuron. And because, again, the input is 0, you'll see that doing the computations, you're still going to get like 0 change in the loss. Now, in this third case, how does this weight affect this loss? Well, it's going to be how this neuron affects the loss times however this weight affects this neuron, which is going to be 0.0098. And we make use of a previously computed gradient, that is this 0.49 over here. And so we populate it in our table. And similarly, we compute it for this weight over here. Now, in this case, it's going to be 0.0098 as well. We do the same for this weight over here and populate it here. Compute the same for this weight here and populate it here. And so we have now computed the gradients of the loss with respect to each of these weights. And we have this table here, which we will save for later. This is like a part of our gradient vector. Now moving on to the previous layer here, right? We want to see how changing this neuron affects the loss over here. That's going to be given by this gradient that is delta L by delta H1 for the second layer. We now use the multivariate chain rule because here, how we get from here to here, it's in two paths, right? So it's through this path, that is through this first neuron here, and it is then through the second neuron here. And it is the sum of their individual gradient effects that we are computing right over here. So in this first term, so we already know how the loss changes with respect to O1. We just write it here. And how the loss changes with respect to O2. We write it here. And we use those values that we have computed in the past, such as negative 49 and positive 49. That's this and this value, respectively. And now we just need to apply how this changing this neuron affects this neuron, which is just going to be like the weight itself, right? That's what we write here. And how the same neuron affects this other neuron in the next layer, which is this weight, 0.8 itself, which is what we write here. Substituting the values, you get 0.7872. And that's why we write the gradient above this neuron to be 0.7872. Next, we perform the exact similar computations, and we see that the gradient here is negative 0.7872. Next, we perform again the exact same computations, but this time you'll see that the gradient becomes 0 here. And it's because like the effects of individual gradients that, the effect of this gradient here through this case cancels out the effects of the gradient here in this case, evidenced by like the negative value and then the positive value. So that means that changing this neuron does not affect the loss at all. Now we go into this previous layer here, neuron. So how does this neuron change affect the loss? Well, it's how this neuron change affects this neuron times how this neuron change affects this loss, given by this. But we already computed that latter part, which is right over here. So now we just need to compute this first part right now. And this is where we run into ReLU, right? Because we know that we have this here is just going to be a ReLU operation applied on this neuron here, which is exactly what the math says here. And so what we want to do is take a derivative of the ReLU. right? So the derivative, it actually turns out if you take the derivative with respect to, that h2 pre, you get 1 for all values of the input greater than 0 and 0 for all other values. And this is, in mathematics, kind of similar. We can represent it by an indicator function here, right? This is just for simple notation. So if this is if this is true, then the value is 1. If it's false, the value is 0. And so we can now use that in our computation here. So we already know this first value, which is, this gradient that we computed previously, which is right over here. And the second value is just going to be 0, right? Because we know that this value is negative 0.02. It's less than 0, and hence 0 is the output here too. So changing this neuron does not affect the loss, and we reflect that in the gradient value right over here. Similarly, we compute the gradients for each neuron in this layer too in a very similar way. But in this case, like the ReLU activation, it's, the derivative is going to be, 1 because it's greater than 0, this activation. And you get negative 0.7872, which we write over here. And similar to the first case, we have the computation become 0, and hence we write 0 over here. And now what we can do is, once again, we now hit another weight layer. And we're going to populate our weight layers. We're going to store them in a table. And I've put 9 values here. So how does this weight change this loss? It's how this neuron changes, this loss times how this weight changes this neuron. Exactly given by this computation right over here. And if we already have pre-computed values, which we use. And hence, we get 0, which we populate in the table. Second case too, we use this pre-computed value here and then multiply it by this input 0, and you get 0. Similarly, again, pre-computed value 0 multiplied by 0, we get 0. Pre-computed value 0 multiplied by 0.04, you get 0. In this case, you have pre-computed value negative 0.7872. You multiply it by, the 0.04. You get this negative 0.03488 right over here. And in the other cases, you'll see, you can just keep multiplying it by 0 because either the input is 0 or the gradient is 0. And so we get this table over here, which again, we append to our gradient vector calculation. This is a part of our gradient vector. Next, we'll go to the previous layer here. How does this neuron now affect this loss? Well, it's how this neuron affects the loss, whatever the effects are, times how this neuron affects this neuron, plus how this neuron affects this loss, times how this neuron affects this neuron, plus how this neuron affects this loss times, this neuron, how it affects this neuron. That's exactly given by this chain rule right over here. And we sum the effects of those gradients. Now, 3 of these gradients have already been pre-computed, which is great, so we can just use them over here. And then the other cases are just like the weights that connect them. That's what happens when you compute these derivatives. And then you'll get negative 3936. And so that is what we write as the gradient over here for this neuron. So if we change this neuron by 1 notch, the loss will decrease by 0.3936 notches. We do then the same exact calculation for this second case over here. Very similar computation, and we're actually going to get a very similar gradient calculation output. And then similar for this third case as well. Now, going back to the previous layer over here, how does this neuron affect this loss? Well, it's given by how this neuron affects the loss times how this neuron affects this neuron here, given by this calculation. Once again, because of how we've already pre-computed this value over here, we just need to compute this one value of gradients over here, which again is similar to our ReLU activation. It's just, the output is simply going to be like an identity, which we can then use in our calculation, and we get this wonderful value of 0 over here. So the gradient of this is now 0. So changing this neuron does not affect the loss, at least for this example. Next, we do the exact same thing. We're changing this neuron affects the loss by 0.3936. And similarly for this last case, we can also make the computations to get the gradient here. And now we have our last set of weights that we need to compute the gradients for. And so what this becomes is, well, how does this weight affect the loss? It's how this neuron affects the loss times how this weight affects this neuron. So we already know one thing is 0 here, so it's going to end up to be 0, which we populate in the table. Similarly here, it's going to be negative 3936 times 0.3. That's over here. And then it'll be 0 here. This is again negative 3936 times 0.5, which we populate in the table. And then it's going to be 0 here too, because the gradient here is 0. And so what we have here is we have the gradient updates, or like the weight updates of how every single weight affects the loss here. And we've written it out in 3 tables. But in reality, like we mentioned before, this can be used to compute the gradient vector, which we have over here. So the gradient vector, now evaluated at these current parameter values, will be, the values that we just computed in the table. And this vector will give the direction of steepest ascent. But because this is a cost function, we know that, well, we don't want to just ascend with this cost function. We want to descend, and hence we use this negative value. How much we want to descend, we use a learning rate. And let's just right now just say that this is going to be 1, and then we will update all of the weights simultaneously. So now if we do the computations here, you'll see that, every weight is going to be the weight minus the gradient of the loss, like how much the loss was affected, right? And in doing so, you'll see that, well, for this weight 1, 1, that's this weight over here, it's going to be that weight minus whatever we computed in this table over here, right? For the first table, right? So it's still going to be 0.2, which means the weight doesn't change. But now this second weight over here, which is 1, 2, the weight is negative 0.2, which is over here, minus whatever the gradient we computed, which was over here for that weight 1, 2. And so we apply that and you'll get this new value. And so you can compute this new weight value for all of these cases over here. And then you can see that, well, we've updated the weight accordingly. Next, we'll do it for the second layer. Now for the second layer, we do all the computations over here, and you can see that only one of these weights is going to be updated. That's 0.531488, which is exactly this weight over here, and so we have updated that weight. And then for the third layer, we see that these sets of weights are going to be updated based on these table values here, and we have now also reflected it and updated in this table too. Now, I just want to note that this is just the weight updates of all of these parameters corresponding to one iteration of the backpropagation algorithm. Now, in order to actually verify if all of those values are right, I actually wrote a program that initialized and created a network exactly the same as the one that we saw just now over here. And I also printed out the intermediate activations after making a single iteration. So I'm printing out, the initial parameters, and then I'm, conducting a single backward pass right here, an optimization step. And then I'm going to be printing out the weights after that, right? So the initial parameters is exactly as we saw before. Now you can kind of see the activations. It's very similar to what we computed previously. And you can also see that these weight updates over here, they are exactly the same as what we see in the new weight updates too. So all of this, kind of also helps me corroborate that the values that we computed by hand are exactly reflective of how, this optimizer is actually learning and how backpropagation is actually working. So I hope all of this makes sense. Quiz time. Have you been paying attention? Let's quiz you to find out. Why are we performing backpropagation? A, to approximate the loss function. B, to remove negligible weight connections between layers. C, to speed up computing gradients for a large number of parameters, or D, to improve model performance over training time? I'll give you a few seconds to answer this question. The correct answer is C, but can you tell me why? Give your reasoning in the comments below and let's have a discussion. And at this point, if you think I do deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do for quiz time, but before we go, let's generate a summary. So in this video, we took a look at a definition for backpropagation and also understood why exactly we are performing backpropagation too. We then took, our simple neural network here, broke it down into individual components, and then we performed like a forward pass and as well as a backward pass throughout, right? With a lot of these computations. And then we also verified what we did with a program that we wrote in order to make sure that the values are correct. So that's all that we have for today. I hope everything made sense. And once again, I'm going to encourage you that while watching this video, you really only do learn about this computation if you do it by hand. But hopefully this video gives a general guidance in how you can get started with it. So I hope it helps. That's all that we have for today. I'm going to be linking down some proofs of why chain rule exists and is a thing down in the description below. And if you want to learn more about why we have backpropagation that we do in the way that we do today, please check out this video and I will see you in the next one. Bye-bye.